There we go. All right. So apologies for the technical delays. So today we're going to talk about Openmp, which is an alternative parallel programming specification. 2 weeks ago, we talked about the message passing interface, which is the most popular distributed parallel programming API. Today we're going to talk about the most popular shared memory API, which is Openmp. So I'll go through an introduction at first, then I'll talk more about the Openmp spec itself. It's actually pretty straightforward and relatively short compared to message passing in particular. I'll talk about some of the new features and more recent versions of Openmp, which helps to give you an idea on where it's going. Unsurprisingly, a lot of that is GPU oriented. And then I'll go through some practical examples at the end. So Openmp is not to be confused with Openmp Api, which is an open source software pack implementation of the message passing interface. Openmp is the open spec for multiprocessing. It has nothing to do with MPI whatsoever, although it can be used in conjunction with MPI, as I'll talk about more towards the end. So this consists of mainly a set of compiler directives, which are most of what most applications end up using. It does have a small runtime library or API that you can use. You don't actually have to use that. And it has some environmental variables that get used to control the runtime execution. The original specification is for C, C++, and Fortran. It does require a compliant compiler. Just about every modern compiler is now compliant with some flavor of Openmp. And it's been a joint effort developed over the last few decades by academics and the major hardware and software vendors. And the main landing page for Openmp is, unsurprisingly, openmp.org. So it's been around for a long time. It's a little bit younger than message passing, but not by much. It's been around for about a little over 2 decades now. The spec used to be split between the languages. It no longer is. Now it's unified. One of the strengths of Openmp, probably its best strengths, is it's relatively easy to use. And you can incrementally parallelize an application. I'll show you how to do that with some specific examples towards the end. Depending on the application, of course, it can be fairly easy to get a parallel speedup with Openmp. And it is potentially scalable as long as you have a large shared memory machine, right? So you will be limited to one machine with Openmp. You can't actually use Openmp over a network. There have been a few projects or products that have tried to create virtualized pools of shared memory across machines over a network, and they have not worked out particularly well. That doesn't mean that it won't work out for somebody in the future, but right now there's no real good way to do that. So it will be limited to a single system. The plus side, of course, is that most architectures are evolving towards this design, right? We keep getting more and more cores per machine. So this plot I actually lifted from one of the NERSC workload reports. If you're not familiar with NERSC, it's the National Energy Research Scientific Computing Center at Lawrence Berkeley National Laboratory. This is run by the US Department of Energy, Office of Energy Sciences. It's the main open resource for scientific computing within DOE. They do a really good job of capturing their workload. So you can see that from this slide, they don't even bother asking if people are using MPI because everybody's using MPI. But closely, number 2 after MPI is Openmp, which is used by something like 85% or so of applications. And then you can see GPUs are starting to climb just behind that. So the Openmp design goal, this is thread-based, right? So a single process will access shared memory and have multiple threads. And Openmp gives you the ability to control and use those threads. It is still explicitly parallel, right? It's not automatic. If you use the auto-parallelizing feature of a compiler, which somebody asked me about in the MPI talk a few weeks ago, it will do something very Openmp-ish to your code. But with Openmp, you still have full control over what's going on. And that's mostly through compiler directives, as we'll go through here in a minute. You do have the ability to dynamically create and tear down these thread teams. You don't necessarily have to use the same number of parallel threads all the time. So my little cartoon picture to illustrate this, and my uninventive name for the executable called a.out. You've got some shared memory data in there. And then when you enter a parallel region that has been parallelized with Openmp, it spawns a thread team. And then at some point at the end of the parallel region, you can actually have that thread team collapse back down to a single thread again. That can be all of your application, that can be portions of your application, that part is entirely left up to you. The idea behind this cartoon is this is a shared address space, right? All of these parallel threads can access the data in your program. And of course, as I said before, this is limited to a single machine. And GPUs follow this basic same model. They are basically highly threaded, parallelized instruments of their own, but that's a separate conversation. Contrast this with the other cartoon that I showed you a few weeks ago, which is the message passing model. Remember, the message passing model is multi-process, right? So you have many independent processes. They don't have to be on the same machine. They can be distributed across a wide area network. And they basically share data through messages and not through directly accessing the memory of the other processes. So going back to what I said before, that computer architectures have been evolving this way for some time. This is basically a chart showing roughly 4 decades of CPU trends. So up at the top there, the gold triangles are the transistor counts. You can see Gordon Moore's prediction there that the transistor count basically doubles every 18 to 24 months. That has held true more or less since 1970. We're going to get close to the end of that here in the next few years, maybe the next 4 or 5 years, but has still been exponentially increasing all this time. Now, if you drop down to the green squares there, you can see that the frequency for these CPUs is topped out, right? Unless you resort to heroic measures like cryogenically cooling your CPUs, you're not going to get a CPU that runs faster than 4 gigahertz, give or take a little. And that's been true for almost 20 years now. So where has all these extra transistors gone? Well, if you go to the blue circles there in between, you can see some of the effort has gone to improving the single thread performance. Now there's only so much you can do to improve that given that your frequency stays the same, but you can do instruction level parallelism or vectorization to increase that. And you can see that that curve has been slowly increasing over the years too. And all of this, of course, is capped by the power limit, right? The red upside down triangles there. Again, unless you're cryogenically cooling your CPUs, and even if you are, there's a limit to how much power you can actually take off of these systems in a given rate of time. So finally, the curve on the bottom there, all the black dots, those are all the extra cores that we're getting. So that's where almost all of the extra transistors are going, right? Now we're buying machines that have 32 or 64 or even 128 cores on them, and GPUs have even more cores than that. And that slide basically just says everything that I just said in the plot there. So the good news is that computer architectures are making it more and more practical for Openmp type applications, right? You can get an awful lot of performance out of a single machine now without necessarily having to use message passing to parallelize across multiple machines. So before we get into the details here, the Openmp general syntax is actually very simple, right? For C and C++, it's a pragma. Pragma, OMP, and then the construct, where the constructs we'll get into here in a minute. The constructs have some optional clauses that you can specify, and that's how you construct your parallelism in your code. If you're in Fortran, it looks like a regular comment symbol and then $Openmp, and then the construct and clauses. And the construct and clauses are the same, regardless of which language you're talking about here. Some are more applicable to certain languages than others for specific features, but we'll only talk about the ones that are common to both. So the good news here is if your compiler doesn't support Openmp, or if you want to turn Openmp off, you just flip a flag on your compiler and it will just ignore them, right? Because it appears as a comment otherwise. So that's quite handy. And that's where part of the incremental approach to parallelization comes from. So if you look at the components of Openmp, the big square I'm showing in the middle there are the directives, right? The pragmas. And we'll go through those in detail, but there's actually not that many of them. The smaller runtime library, you're free to ignore. I'll show you some examples of using those, but you don't have to use them. Most applications do not. The Openmp environmental variables are basically just a way for you to control the runtime system. So there's only a few of those too. So let's talk about these smaller pieces first then. Let's talk about the runtime library and the environmental controls. The API itself is relatively small. It's not like MPI where you're talking about hundreds and hundreds of functions, a certain number of which are absolutely mandatory. For Openmp, they are entirely optional. But they have the same functionality, right? It gives you the ability to control and query your parallel environment. So you can monitor how many threads you have, what the thread IDs are, how many processors are in your box. You can adjust the dynamic parallelism, the nesting. There's some lock functions if you're writing a library. So there's a certain number, but it's on the order of tens and not hundreds and hundreds of them. Unsurprisingly, the header file that you need to include for C and C++ is named omp.h. And once you have that, then you have defined all of your functions. I'm just showing omp setNumThreads, which, as you can guess from the name here, it actually sets the number of threads in your parallel regions. If you're in Fortran, you use omp_lib for accessing the API. So I'm just going to show you a short list here of the core Openmp API functions. OMP set num threads we showed before. Get num threads, as you might expect, gets the total number of threads. Get the max number of threads. Get my thread number from within a parallel region. Get the number of processors max. The list goes on. Right? These are meant to be self-explanatory, and they mostly are. One handy one I want to point out in detail, though, is of course the high-resolution timer. Like MPI_W time, it's OMP_get_W time for the wall clock timer. W tick if you want to get the resolution of the timer itself. These behave just like timing calipers, like they do in the MPI case. So if you've got a chunk of code that you want to time, you just insert them around the chunk of code that you want to time. And that's pretty much it for the API. Like I said, it's pretty straightforward, especially compared to message passing. For the environmental controls, the one that you really want to remember is that first one, which is OMP_num_threads. That's just an integer, and that's how many default threads are used in your parallel regions. Depending on the complexity of your application, you're probably using the same number everywhere, although you certainly don't have to. You can also control the schedule by default. We won't have too much time to talk about that today, but that's just how the threads get scheduled to run in the runtime environment. And then some options for turning on or turning off dynamic thread management and nesting. One thing I want to point out here in detail, though, that we'll come back to a little bit later, is that the vendors usually have some additional environmental variables. This is particularly true for Intel, so I'm going to call that one out specifically when it comes to how the threads get placed on the CPUs, which, as you can guess, is fairly important. And of course, an example of how to set these. If you're in Bash, most people are in Bash, you just export name of the variable and then the setting that you actually want to use. Okay, so that didn't take very long to talk about the runtime library and environmental controls. The vast majority of people will just use OMP num threads for the environmental controls and ignore a lot of the other stuff. And I've got some specific examples coming up here at the end that I'll show you that illustrate this. So let's talk about the directives themselves. Okay, so suppose we have an application, we want to parallelize it. How do we go about doing that? So we have the ability to construct parallel regions. We have the ability to divide sections of this code up by work sharing them across the thread team. And then we've got some of these clauses that we'll turn back to how we control the data environment and especially synchronization. So you can guess what's coming up for the parallel regions. It's just pragma OMP parallel if you're in C++, OMP parallel and N parallel if you're in Fortran. Of course, if you're in Fortran, you have to explicitly declare when it ends. You don't have to do that for C and C++ because, of course, you can use the braces to denote a single code block for those. So I'm going to skip for the moment the data environment clauses that are shown on this slide here, and then I'll circle back to talk about them all at the end. Because as you might expect, these are basically shared in terms of their definitions across all the different OpenMP constructs. Again, the names are meant to be self-explanatory, so as you can guess, and I'll come back to, right, private list just determines that all the variables in that list are private to each thread by default, and shared is the exact opposite. So the loop level parallelism, which OpenMP was originally intended for, is pragma OMP4, or in Fortran OMP do, and then the clauses. That just parallelizes a single for loop or a single do loop. You can also use OMP sections, which is the second block shown here. OpenMP workshare is just a Fortran specific one, so I'll skip that for the moment. The cartoon picture that I'm showing here, right, you're trying to parallelize a work-intensive loop, right? So it's going to be fairly important for your application to determine where it's spending the most time. And that involves profiling the application. And the example I'm going to show you at the end, we'll actually go through that in some detail. So we can see how to actually attack a new code with OpenMP. So if you have a fairly even workload, you're going to actually parallelize it with OMP4 or OMP do. If you have something which is logically broken up into a few sections with an irregular workload, you might attack it with the OMP sections. If you have something that you're going to serialize inside an otherwise parallel region, you would use OMP single. So the OMP4, again, pragma OMP4, self-explanatory. And then the clauses and the constructs we'll go through here at the end. Simple example, if I've got this function, I've got a pragma OMP parallel for this outermost block, Then inside, I've got two separate for loops that I'm going to parallelize. Hopefully n is a large number here, so we have some actual work to parallelize. That's what it usually comes down to for OpenMP, is to make sure you have enough work to actually make it worthwhile to parallelize it. So since these loops are independent, we can actually use this no wait clause that I skipped talking about a few minutes ago. As you can guess from the name, it's going to mean that all the thread teams will proceed past the end of this code block without bothering to synchronize. Right? Synchronizations, as always, are very expensive operations. We'll go into some details about just how expensive they are. If you can get away with it and it's safe to do so, you can specify this no wait to have all the thread teams proceed. And because these are completely independent entities being updated here with no dependencies between them, we can actually get away with that. Sections, again, you can guess what sections look like. No surprises here. How do the sections get assigned? Well, there's an implied barrier at the end of each of these sections directives, unless you use the no wait clause for them. You can't branch out of them, right? That would not make sense to do that. The section directives have to occur within an overall sections directive themselves. If your number of threads doesn't match the number of sections, well, if you have more threads, some get idled. If you have less threads, then it will be left up to the implementation on how to divide the work that gets assigned to them. And then single is the serialization operation, which again, you don't want to use in a parallel code if you can possibly get away with it, because that will impact and greatly limit your speed up that you might actually achieve. And of course, you can combine the parallel regions with the work sharing directives themselves. So if you just have a single loop that you want to parallelize, you don't necessarily have to create an entire parallel region for doing that. You can just do a single OMP parallel and attack that one loop. Of course, you want all of your effort in that code, or as much as possible, to be in that loop if you're going to do that. And then just to go back to my cartoon picture for how we started this, the do for is a data parallelism approach, right? We're going to attack a highly compute intensive loop inside our code and parallelize that. Sections is more of a functional approach to this, right? Break the work into separated discrete sections, each of which will get assigned a different thread. And then single is the serialization operation. All right, so let's talk a little bit more about the data environment. Again, this goes back, this is meant to be self-explanatory. This goes back to the constructs and those clauses and how they get applied. So private and shared determine whether or not the variables in those lists get made private to each member of the thread team or shared amongst them. Thread private basically just takes those named variables, makes it private to each thread, but it's persistent between the parallel regions, right? If you have multiples of them, as long as the thread count stays the same. First private, same as private, but we initialize the values with the value of the original thread. Last private, same as private, but the thread executing the last iteration will update the value of the original object. As you might expect, there is a reduction clause as well. It works just like the MPI case, right? Perform a reduction with that mathematical operator that you give it. I've got a separate slide here that lists them here in a second on the list variables. You can also define your own. There's a copy in, you get used with the thread private to initialize the values in all the threads. Copy private used with n single to broadcast a value from one team member to the others. A little bit more on the reduction, right? A private copy of each of those list variables will be created for each thread, and then the reduced value will be written to the global shared variable at the end of that encompassing parallel region or construct. So these variables have to be named scalars. They're not arrays or structures. They have to be declared as shared, and they obey all the operators that you would hope for. And thankfully, after Openmp 3.1, they finally added a min and max for C and C++. Since C and C++ do not have min and max as part of their standard math library, Openmp had to add special support for them. And it definitely took a while for them to do that. And again, you can actually define your own user-defined functions too, using the declare reduction construct. Okay, so let's talk about some of the synchronization directives. So OMP master, execute that section only with the master thread. OMP critical, restrict access to one thread at a time, otherwise block. OMP barrier, synchronize all the threads at that point. Obviously, that's not something you want to use from the point of view of performance. But you want to keep in mind that a lot of what we've talked about so far, they're actually implied barriers. And we'll come back in a minute here to discuss what the costs of those are. OMP atomic is a special case of critical. The statement following that allows a specific memory location to be updated atomically. And this can take advantage of hardware that can actually do this in a specialized and highly optimized way. So if you have the option, generally you want to use atomic instead of critical. Flush, ensure the threads have a consistent view of all their shared variables at that point. Again, that's not an inexpensive operation. OMP order to execute the code in the same order as if it were sequential. Again, not a performance option, that's a debugging option. OMP single, just make sure you execute that block of code only by one thread at a time. Okay, and that's it for the directives. I don't think that took me too much time. It's a relatively short list, right? We'll go through some specific examples to show how to use these things in practice. Let me talk for a quick minute here about some of the more advanced features that have been added in more recent versions of OpenMP. There's a task pragma that's available now. You can actually use this for highly irregular workloads. Everything we've looked at up to this point has been very directed towards loop level parallelism or functional parallelism. This is more task oriented. You can use this to do a lot of the things and fill in the gaps for what was missing in the constructs that we had before, especially if you want to do something that's recursive, for example. And you can synchronize the task explicitly with an OMP task wait. There has been a considerable efforts in the last year or two to add accelerator support for offload to GPUs. This has been motivated by several things, not wanting to spend too much time talking about the history of this, but let's just say that the major vendors involved didn't necessarily see eye to eye on the best approach to use for this. So there's a separate open source project called OpenACC, which was basically to apply OpenMP to GPUs, and that has basically now been adopted by OpenMP. So there is accelerator support. As we see more GPUs get deployed by, say, Intel, I think we'll start to see a bit more support within the runtime environments too. But right now, the runtime environment support for offload to GPUs is a little bit flaky. The user-defined reduction operations, we talked about those already. There are SIMD constructs where you can use for portable vectorization. Generally, you're probably still better off with the compiler native ones, though. There has been some extensions to thread affinity, some of which I'm going to show you in a minute here. And of course, the task extensions that we talked about before. Okay, so let's talk some numbers here for considerations. So barriers, well, they're pretty much everywhere you'd expect them to be, right? If you're at the end of a parallel region, there's got to be a barrier there. Unless you're using no wait, if you're at the end of a do or for or sections or single, there's also a barrier. And if you're at the end of a critical, there's also a barrier. Flushes occur as well, pretty much again at those same endpoints. So what do these things actually cost? So one advantage of having given this talk for an awfully long time is that I can reach back in my notes and look at some benchmark data from a long time ago. So here's what some of those operations cost in terms of overhead. This was on an SGI Origin 2000, actually just about in the year 2000, maybe 2001. It's almost 20 years ago. These were MIPS processors running at a whopping 250 megahertz, and they had 8 CPUs on there. So these were single core CPUs. So they're able to run on using OpenMP on up to 8 threads, and this is the cost, right? So let's just look at the reduction operation, which tends to be the most expensive. As we go from 1 to 8 threads, we go from 2 microseconds to 30 microseconds. Well, that doesn't sound like an awfully long time until you convert it into the number of clock cycles that you're actually wasting, right? But again, this is overhead. You're probably not doing anything else while this is happening. So you're talking about 7,500 or so clock cycles in lost computation. So you say, okay, great, that was 20 years ago. Well, you can expect what's coming next. So this is what you get when you run it on a newer machine. So these are 32 core Skylake nodes, 2.1 gigahertz. I think we bought these last year, roughly last year. So 2 sockets, 16 cores per socket, 32 CPUs total. The absolute values for these numbers, of course, have all gone down, right? 20 years have gone by. So again, just looking at the reductions, 0.12 microseconds up to 5 microseconds for the full machine. Great, the numbers went down. Yeah, so did the clock rate correspondingly went up by about a factor of 10. So 5 microseconds, now we're at 2.1 gigahertz. We're now losing a little over 10,000 clock cycles in lost computation. So I wouldn't exactly define that as progress, right? What's responsible for this is, of course, the memory subsystems have been lagging behind the improvements in CPUs for a long time. We're only starting to see that addressed now in the GPU age, where the GPUs have enabled faster memory subsystems, and the CPU vendors are just barely starting to catch up. So you have to be aware of these overhead costs, right? Because these will limit the amount of parallel performance that you're able to get from your application. Oh, and that last bullet item I use when I'm giving this lecture a bit more interactively, how does this compare with the overhead for message passing? Well, it depends, right? On the smaller scale, right, the cost to send a message between two machines using MPI is usually about a microsecond or a microsecond and a half using an optimized network, right? So it's actually less than what you see here with OpenMP. But keep in mind that you're talking about 32 cores to hit the 5 microsecond level. Once you get 32 processes involved in an MPI calculation, then you're talking about a latency, which is about the same, if not a little bit more expensive. So one warning before we get into the examples here. Thread safety issues, right? If you're going to use OpenMP with MPI, which is a popular thing these days, you have to use MPI net thread and check your level of thread safety with that. You also have to be aware that thread safety applies to other functions that you might be using, right? Don't treat them like black boxes if you don't know what's going on inside of them. So the example I like to show here is from the random number generator. This used to be the default. Thankfully, it's usually no longer the default that people try to use, called rand. I'm looking at the man page from rel 5, but it's still the same in rel 7. Probably will be the same in rel 8. You'll notice that there's actually 2 forms of this function, right? Regular old rand and then rand underscore r. The underscore r is meant to be the reentrant version. That's the thread safe version. The reason for this is that there's without going into the details of the random number generators themselves, there's a hidden state variable that if you attempt to call regular rand from multiple threads, you're just going to get the same sequence of random numbers for every single thread. And that is going to ruin your statistics, right? You're going to get an incorrect result from that. So you have to be aware of these things that are happening that it certainly won't cause your code to crash, but it will give you incorrect results. A little bit more on thread affinity, right? You want to be aware of this for the same reasons that we wanted to be aware of them in the message passing case, right? You've got contention for the various resources. You want to make sure that your threads are being mapped to the relevant portions of the CPU. The GNU compilers support this as well. Those are these options. They do not expose the level of detail that the vendors do though. So I'll show you the one for Intel. Intel uses KMP underscore affinity as the environmental variable. They will still respect the GOMP underscore CPU affinity. And I think it's actually also now the OMP underscore CPU affinity at a lower level of precedence, but they offer many, many more options. More options than I can safely describe in the amount of time that I have to talk to you here today. There's a link here to the software pages where Intel talks about them, but you can lay this out in excruciating detail for how you want the threads to be mapped onto the CPUs. And depending on what type of architecture that you're actually using, whether or not hyperthreading is turned on or simultaneous multi-threading, no matter what the use case is, you can actually set that appropriately. Okay, so in the last few minutes that we have here, let's go through the examples. So if you want to check the compiler support, you can go to this web page to check that. It should be a fairly up-to-date list. If you want to do hello world in OpenMP, you're going to have to use the API. This is one of those cases where you do have to use the API. So I've got a parallel region here with each thread ID made private. I print hello world from thread X, and then down below I've got a only from thread 0 print out how many threads there are total and how many threads are on the box. And if you want to compile and run that, well, if you're going to use the GNU compilers, it's just -f OpenMP to enable the OpenMP. And then we set the number of threads we want to run, and then we run it, and it tells us how many threads we have, what each thread ID is, and there's 32 cores available on the front end machine that I'm running this on. If you want to do it with the Intel compilers, you just change the flag. It's -q OpenMP instead of -f OpenMP. Otherwise the same. Okay, so let's take a real example, or at least a less trivial example. We'll take a sample molecular dynamics code from openmp.org. It's a fairly small Fortran code, does a fairly simple harmonic potential between particles, and just runs molecular dynamics on them. We're going to profile it first to see where it's spending its time, and then we're going to instrument it with OpenMP and see what kind of speed up we get. Okay, so we grab the code. I changed the number of particles in the code. I think it defaulted to 500. I made it 5,000 to give it a little bit more time. We're going to turn on profiling. If you're using either the GNU compiler or the Intel compiler, or in fact every other compiler I can think of, it's the -p option to turn the profiling on. And then we want to use the -g option to enable symbols so we can actually do a line level profiling on it. Then we run our application after we compile it with the profiling enabled. It will produce a little statistical profile called gmon.out. And then we feed that into gprof, which is the GNU profiling utility. So we're going to turn on the line options for this. It does produce a copious amount of output. I'm only really interested in the top part, so I'm going to redirect it to a file and then look at the top of that file. And we see that looking at our profile here, it spends more than 90% of its time in these 6 locations in the code. And these 6 locations are actually clustered around 2 locations. And this being a molecular dynamics code, it's no great surprise what those locations look like. One is the definition of the potential and the force, again, which is just a simple harmonic potential. And then, of course, the call over particles calculates the distance between them and then updates the potential and kinetic energy based on those forces. So if we're going to parallelize this with OpenMP, it's pretty easy, right? We're just going to take this outermost loop and parallelize that guy. So if I do that, it's as simple as adding those 5 lines that you see there at the top. So a single merged parallel do. We'll set up our default shared and private variables. We'll do a reduction on the potential and kinetic energy. And that's all we're going to do. We'll just add those lines and run with that. So I created a Slurm script to actually run a scaling study all in one go. Generally speaking, you don't want to compile things inside Slurm. It's a total waste of time. And if there's an error, it will be a real pain to debug. But I'm showing that just for completeness here so I can squeeze it all in one slide. So I compile my regular serial binary there. I compile my profiling binary, and then I compile my OpenMP binary. And then down below, I run the serial run, and then I do my speed up runs all in one go on a 32-core Skylake system, the kind that we were talking about before. So having said all that, having done all that, what do we get? So this table shows the timings. Serial time, it's just a little about 25 minutes or so. Running the OpenMP code on one thread. This will tell us what our overhead is. You can see that we've got about 13% overhead, right? So my speed up on one thread is only 0.87, but then it takes off after that, and going out to 32 cores, we get a speed up overall of about 21 or so. So that's not too bad for having invested such a modest amount of effort, right, to parallelize that application. So last but not least, let me tie this back to the talk I gave a couple of weeks ago about MPI. You can actually combine MPI with OpenMP, right? This is a fairly popular thing to do now, right? You want to take advantage of MPI for message passing between machines and then OpenMP within the machine. And this is when the thread and process affinity gets very, very important to make sure that you do it right. So I showed this example 2 weeks ago. I'm just going to repeat it again here. This is the high performance conjugate gradient benchmark. You can find the link in the slide here. The Slurm script just runs it on 2 nodes. The optimal way to run this code is to put 1 MPI task per socket and then fill up the cores on each socket, there's 16 on these nodes, with OpenMP threads. So that's exactly what we're going to do. We set the MPI debug value to be 4 here. That will turn on a lot of helpful MPI debugging. Down below, I'm going to use the Intel KMP affinity setting for the recommended form for this, which is verbose to tell me where it's putting everything. The granularity is fine. It's going to do that for each thread. It's going to put them on neighboring threads per each socket. And then the next 2 settings are for controlling it for hyperthreading, which doesn't actually matter on the CCR machines anyway. And then it goes ahead and runs the application. And when I see it run, I can actually watch it with HTOP, and I see all the cores get filled up as I expect to see. And up at the top, I see my 2 MPI tasks, and I see my 16 OpenMP threads running on each one. And then in the text output, I should see all that helpful verbose output that I expected it to see. And down here for the KMP affinity settings, you can see that it assigned each task to respect each one of these sockets. And that's how they're laid out. Okay, so if you want more information on this, there's a great deal more detail on the Freshdesk page in our training documents. Exceed also has a very extensive set of training documents as well if you want to follow those. And then the upcoming talks next week, we've got an introduction to Perl, and then an overview of visualization the week after that, Singularity the week after that, and then the week after that, storage and quotas before we need to recycle the topics. So apologies for going a few minutes over time, but hopefully only a few minutes. Oops, didn't mean to do that. I can take any questions that people might have.